So in this lecture, I will consider finite dimensional normed linear space. So X will be a normed linear space over a field K, which will be either the real numbers or the complex numbers. So I'll start with the definition. I will say that a set of elements Z1, Zn, elements of X, are linearly independent so linearly independent if there is a unique solution to the equation alpha j zj, sum from 1 to n equal to 0, so that this implies that alpha 1 is equal to alpha 2 equal to alpha n equal to 0. So they are linearly independent if the unique solution of this equation is the equation alpha is the solution alpha 1 equal to alpha 2 equal to alpha n equal to 0. And an observation, so now if you have an element x of x which can be written in two ways as sum from 1 to n of alpha j zj. So here alpha j and of course these alpha j's are elements of K. I didn't say it, but I hope it's clear. So we are taking a linear combinations of the elements Z1, Zn, and I'm saying that the unique solution of this equation is all alphas equal to 0. Now I'm saying remark, if you can write X as a sum of alpha j, Zj, and X as another sum from 1 to n of beta j, Zj. So if you can write in two different ways, well, this, of course, implies, and if Z1, Zn form are linearly independent, so, of course, this means that alpha j is equal to bj, because by subtracting, you get that beta j minus alpha j times Zj, the sum, is 0, and from this you get that bj minus alpha j is equal to 0, which means that alpha j is equal to beta j for all j's. So this means that the representation of X in terms of Z is unique, and I will represent these coefficients as alpha j x. So whenever Z1, Zn are linearly independent and X can be expressed as a linear combination of Z, this expression is unique. So all these coefficients are uniquely determined. So a new definition. So you have a normed linear space X, and I would say that if Z1, Zn, you have a set of linearly independent elements. So consider a space X. You have a family Z1, Zn of linearly independent elements of X. I will say that this set is maximal well if any element X of X can be written as a linear combination of Z1, Zn. So for all X in X, there exists alpha 1, alpha n in K, such that X is equal to the sum of 1 to n alpha j Zj. So this means that the set is maximal if any element of X can be written as a linear combinations of the elements Z1, Zn. And then an important remark is that, well, this number, it's uniquely determined, which means that assume that you have X linear space and that Z1, Zn, and W1, say, Wm, are maximal sets of linearly independent elements of X. So I'm assuming that Z1 and Zn form a maximal set of linearly independent elements of X, and that W1 up to Wm also form a maximal set of linearly independent elements. Then what I claim is that, well, the cardinality of these sets are the same, which means that n is equal to m. And so let me prove this claim. Well, I know that if I consider W1 it's an element of X. Z1, Zn, it's a maximal set of linearly independent, which means that I can write W1 in terms of this as a linear combination of Z1, Zn. So that this means that there exist coefficients A1, J, such that W1 can be expressed as a sum, a linear combination of Z. So here Z, J, it's going from 1 up to n. And, well, the same thing can be repeated to W2 up to Wm. So I can say that, well, Wk can be written as a linear combination of Z1, Zn, and I will write these linear combinations as A, Kj, Zj. Well, on the other hand, W1 up to Wm is also a maximal set, so I can write any of the elements Z1, Zn in terms of linear combinations of W's. So I can write Zj as a sum of L going from 1 up to m of Bj, L, Wl. Because W1, Wm form a maximal set. So now, if I replace Zj in this equation by this expression, what I get is that Wk, it's equal to the sum j from 1 up to m of A, K, J. Now, Zj, it's equal to this sum. So I have a sum from L from 1 up to m of B, J, L, W, L. Let me invert the order of summation so that this is a sum from L from 1 up to m. And now I have a sum from j from 1 to n of A, K, J, B, J, L. But this is the product, if you consider A as a matrix and B as a matrix, this is the product of the matrix A with the matrix B computed at KL. Well, but now I can rewrite this identity saying that I just want to subtract Wk at all sides. So this gives me that 0, it's equal to from the sum from 1 up to m of A, B, KL minus, well, 1 if k is equal to L. So let me write this WKL, WL. Right? This symbol, it's equal to 1 if k is equal to L, and if it's 0 otherwise. So in this sum, the only term which will appear is the one in which L is equal to K, and this will give me minus WK, which is exactly what I had before. Therefore, I have that 0, it's equal to a linear combination of WL. And since the W's are assumed to be linearly independent, this means that all these coefficients are equal to 0, which means that AB computed at KL should be equal to delta KL. And this holds for all L and for all K. So here I started with WK. I can run K from 1 up to M. So this holds for all K. And from this equation, therefore, I get that the matrix AB, it's equal to the identity. Because, well, this is the identity. K and L are running from 1 to M. So this is a matrix which is M by M, and which is equal to 1 on the diagonal and 0 outside. So the conclusion from this computation is that the matrix AB, the product of the matrix A with the matrix B, it's equal to the identity. But A, it's a matrix which has K is running from 1 to M, so it's a matrix M by N, while B, it's a matrix N by M. Now, if you have product of a matrix M by N with a matrix which is N by M, which gives you the identity, this is an exercise in linear algebra. This implies that M has to be equal to M. So I leave to you to show that if you have two matrices, A and B, which are one which is M by N and the other one N by M, and if the product of this matrix is equal to the identity, then you have M to equal to N. And this is exactly what we wanted to prove. We wanted to prove that the number of these, well, the cardinality of these two sets are the same. So this proves that this cardinality, that N is equal to M. And therefore, if you have two different sets which are linearly independent and maximal, the number of elements of these two sets should be equal. And this is what I will define as the dimension of X. So definition, the dimension of a set of a linear space X is the number of elements of a maximal set of linearly independent elements. Well, because we've seen that the number of elements of these sets are the same, so they depend only on the space X, and this is what I will define as the dimension, the algebraic dimension of X. Of course, it is possible that you don't have finite. So I'll say that the dimension of X, it's equal to plus infinity if for all K larger than 1, there exists a set of linearly independent elements with Z1, Zk. Because maybe for any K, you can find K linearly independent elements, And in this case, you'll say that the dimension of X is plus infinity. But if there exists a K, well, if the maximal number of linearly independent elements is finite, equal to K, we will say that this is the dimension of X. And in this lecture, I will concentrate it on sets X whose dimension is finite, so sets X for which there exists a finite maximal set of linearly independent elements. Now let's consider a space X, which is a normed linear space. Let's assume that the dimension of X is equal to n, which is finite. And therefore, I know that there exists a maximal set of linearly independent elements, which I will represent by Z1, Zn. So any element of X can be written as a linear combination of Z1, Zn. So if I take X, I know that I can write X as the sum from 1 to n of alpha j x zj. And these coefficients alpha j x are uniquely determined. So they are well defined. And my claim is that there exists a constant C0, which is finite, such that the sum from 1 to n of the absolute value of alpha j x, that this is bounded by C0 times the norm of X. So X, it's a normed linear space. It has a norm. I'm representing by the symbol norm. And what I'm claiming here is that, well, this sum, it's bounded by a constant times the norm of X. At this point, I suggest you to try to solve, to prove this statement to understand better what, well, the solution I will present now. So I will proceed by contradiction. So it's a proof by contradiction. So I'm assuming that it's not true. If it's not true, this means that there exists, for all p larger than 1, there exists an element xp such that the sum in J of alpha j xp, it's larger than p times the norm of xp. So for all p, there exists an xp in this space X for which this holds. So let me define alpha p to be xp divided by this number. Right, so now what I claim is that if you write alpha p on the basis zj, what I get is that the alpha j of yp, it's equal to alpha j of xp divided by this number. Maybe, okay, let me sum over k now. Alpha k xp. And this is clear, right? If you take an element xp, an element x, you divide it by a scalar, then the coefficients you get here are exactly the original coefficients divided by the factor which you multiply or divided your element. So if I'm taking xp, I'm dividing by this quantity. In my expressing this new element of yp in terms of zj, what I will get are the original coefficients divided by this number. So this is what this is saying. And this means that now if I take the absolute value of alpha j yp and I sum, what I get is 1. So this is 1. And on the other hand, so if I consider this inequality and I divide this inequality by this quantity, on the left-hand side, I get that this is, so let me divide this inequality by this expression, so I get that 1. It's larger or equal than p times the norm of yp, right? Because the norm of yp is this expression, it's equal to the norm of this expression, so this is the norm of xp divided by this sum. And this is exactly what we get, and this means that the norm of yp, it's bounded by 1 divided by p. Right? So up to this point, I started from this sequence, and from this sequence, I defined a new sequence, which is yp. And this new sequence yp has two properties. First, the norm of yp is less or equal than 1 divided by p for all p. And on the other hand, the sum of the absolute values of alpha j yp, it's always equal to 1. From these two properties, I will get a contradiction. Well, on the one hand, if I take alpha 1 of yp, well, this sequence, as a sequence of p, it's bounded by 1. Well, because the sum, it's equal to 1. And therefore, I can, well, since I have a sequence of real or complex numbers bounded by 1, therefore I can extract a subsequence which is convergent. So I can extract a subsequence pk from the original sequence for which alpha 1 of ypk is convergent. And I can repeat that for alpha 2, taking a subsequence and proceeding in this way for all the n sequences. I can find a subsequence pk, or maybe pl, such that alpha 1 or alpha j y pl converge to some alpha j for j between 1 and n. Okay? From the fact that it's bounded, I can extract subsequences which are convergent. Well, but ypl, it's equal to the sum from 1 to n of yj alpha j ypl zj. And since these coefficients are converging, as L goes to infinity, this sequence, this linear combination of the elements Z converge to the element alpha j zj. And I also know that, well, since the sum from 1 to n of the absolute value of alpha j yp, it's always equal to 1, by taking the subsequence pl here and taking the limit in L in this identity, what I know also is that the sum from 1 to n of alpha j, it's equal to 1. Fine. So I have two informations. Here I have first that the sequence ypl is converging to alpha j, the sum of alpha j zj, and that the sum of the absolute values of alpha j is equal to 1. On the other hand, from this inequality, by taking the subsequence PL, well, or by observing this inequality, what I obtain is that as P converges to plus infinity, the norm of Yp is going to 0, which means that Yp is converging to 0. So on the other hand, from that inequality, I also have that Ypl, it's converging to 0. And here I get a contradiction, because on the one hand, I know that Ypl is converging to this vector, to this element, which is, let me call it y. On the other hand, the same sequence, it's converging to 0. This means that y has to be equal to 0, so that this linear combination is equal to 0. But now, since z1, zn form a linear, well, are linearly independent, this means that if this sum is equal to 0, all coefficients alpha j have to be equal to 0. And this is in contradiction with the fact that the sum of the absolute values is equal to 1, right? So from this inequality, I conclude that alpha Ypl converges to 0. But from the first one, I know that y can't be equal to 0 because the sum of the absolute values of alpha j equal to 1 and z are linearly independent. So we get a contradiction, and therefore from this contradiction, we have proven that there exists this finite constant such that this inequality holds. So X is still a normed linear space with finite dimension, Z1, Zn, a maximal set of linearly independent elements. And we just proved that there exists a finite constant C0 such that if I write X as a linear combination of the elements Z1, Zn, then the sum of the absolute values of alpha jx is bounded by C0 times the norm of X. And now my claim, my lemma, is that, well, if I represent by B01 the unit ball, so this is the set of all points x in X such that the norm of X is bounded by 1, well, that this set is compact. And the proof, well, it's quite simple once you have that inequality. So let me consider sequence xp in this set. So let's assume that the norms of xp, the sequence, are bounded by 1. Now, from this inequality, this implies that alpha j xp, the sum from 1 to n, that this is bounded by C naught times norm, but the norm, it's bounded by 1, so this is bounded by C0. So this means that the sequence alpha j xp, it's bounded by 1 for all j. So this is for all p, alpha jx, it's bounded by 1, and this holds for g from 1 up to n. Therefore, I can find a subsequence, PL, such that alpha j x PL converge to alpha j as L goes to infinity, right? This is a bounded sequence of real or complex numbers, so I can always, since the unit ball in R or in C, it's compact, I can always extract a converging subsequence. And once you have this convergence subsequence, what you obtain is that XPL, which is equal to alpha j XPL times Zj, since the coefficients alpha j XPL converge to alpha j, as L goes to infinity, this converges to the sum of 1 to n alpha j zj. And this proves that all sequence xp has a subsequence xpl which converges, which prove the compactness of the unit ball in the case of finite dimension normed linear spaces. Note that, let me call this point a point, let's say y. Note that y belongs to the ball of center at the origin with radius 1 because, well, the norm of y, it's bounded by the norm of y minus xpl plus the norm of xpl, right? This is by the triangle inequality. Well, the norm of xpl, it's bounded by 1, while since xpl it's converging to y, the norm of xpl minus y, this is converging to 0, and from that we get that indeed the norm is bounded by 1. So we have not only proved the existence of a subsequence which converge, but we also proved that the limit point belongs to the same set. So now let me prove that in finite dimensional sets, all norms are equivalent. So again, X, it's a normed linear space with finite dimension, and Z1, Zn is maximal set of linearly independent elements. And my lemma is that all norms are equivalent. So X has a norm. And now we will define a new norm, which I will represent by 0. And I will show that this norm 0, it's equivalent to the norm. And what is the 0 norm? Well, you consider X. You know that X can be written as a linear combination of the elements Zj. And this linear combination is unique. All these factors are unique. We've shown that. Well, so I'll define the norm 0 as the sum of the absolute value of the factors, of the coefficients. So I leave it to you to show that 0 is a norm. So to show that defined in this way, all the three properties of a norm are satisfied. What I will show is that, well, this norm is equivalent to the norm of the space. One inequality is very simple. What I claim is that X, so there exists a finite constant C0, such that the 0 norm is bounded by this constant times the norm of X for all X in X. And this is, I'm sorry, what I want to prove is the opposite. What I claim is that it's very easy to prove, it's the opposite. So there exists a finite constant for which the norm is bounded by C times the 0 norm for all elements X. And why is that so? Well, just write the norm of X. X can be written in the, as a linear combination of Z in this way. So now by the triangle inequality, this is bounded by the sum in J of alpha J X, well, norm of alpha Jx Zj. This is equal to the sum in J of alpha Jx, the norm of Zj. And this is bounded by the maximum of the norms so the maximum for j running from 1 up to n, times the sum of k running from 1 to n of alpha k x. But this is exactly what we defined as the zero norm of x, and this is our constant C0. So we indeed proved that there exists a constant C0, which is given by this maximum, which is finite, for which the norm of x is bounded by C0 times the zero norm of x. So we want to prove that all norms are equivalent. We defined this zero norm, and we proved that the original norm is bounded by a constant times the zero norm. Now I want to prove the opposite inequality, which is that the zero norm is bounded by some constant C1 times the original norm. And again, I will proceed by contradiction. So I'll assume that this is not true, so that for all p, there exists xp such that the zero norm of xp is bounded by p times the norm of xp. And again, let me define a new element, yp, which is xp divided by the zero norm of xp, the zero norm of xp. So we get that the zero norm of yp is just equal to 1. And while the norm of yp, which is equal to the norm of xp divided by the zero norm of xp, so this is bounded by, you see from this inequality, this is bounded by 1 over p. So we have introduced a new sequence, yp, whose zero norm is equal to 1, and whose norm is bounded by 1 over p. Now, yp, the zero norm of yp, by definition, so let me write yp as a sum linear combination of the linear independent elements zj. And what we know is that its zero norm is equal to 1, which means that the absolute value of the sum of the absolute values yj of yp, that this is equal to 1. So again, we can obtain a subsequence PL such that yj, ypl converge to alpha j. And since ypl is converging to alpha j, this means that ypl is converging to y, which is equal to the sum of alpha j zj. Furthermore, since the sum is always equal to 1, the limit is also equal to 1. So we know that the sum of the absolute values of alpha j, so that this is equal to 1. On the other hand, since yp, the norm of yp is bounded by 1 over p, this means that y over pl, it's converging to 0 in the space X for the norm. And here we have a contradiction, because on the one hand, ypl it's converging to 0, and on the other hand, ypl it's converging to y, which is given by this sum. And this y can't be equal to 0, because if it were equal to 0, this would imply that all alpha j's are 0, because zj's are linearly independent. But we know that the sum of the absolute values of alpha j are 1. So y cannot be equal to 0, and from this we get a contradiction. on the one hand, it converges to 0. On the other hand, it converges to y, which is different from 0. And therefore, by contradiction, we conclude that there must exist a constant C1 for which the 0 norm is bounded by C1 times the norm. This proves that the 0 norm is equivalent to the norm of x, because we have both inequality. The norm of x is bounded by c times the 0 norm. The 0 norm is bounded by a constant times the norm. So these two norms are equivalent. And from this, we conclude that all norms are equivalent, which means that in a finite dimensional space, all norms are equivalent. Let me conclude this lecture with a lemma which states that all finite dimensional spaces are complete. So X is complete. Which means that in finite dimension, all normed linear space are actually Banach spaces. So the proof is also, well, you will remark certainly that we used essentially a unique argument in all these proofs. So here again, I'm using the same argument to show that X is complete. To prove that X is complete, consider a sequence xp, which is Cauchy. This means that for all epsilon, I can find n naught, such that if p and q are larger than n naught, then the distance between xp and xq is bounded by epsilon. But since the norms are equivalent, I know that the norm, the 0 norm, it's bounded by a constant times the norm. This was the previous lemma. This means that this inequality holds modulo a constant for the 0 norm. So I know that xp minus xq, 0 norm, it's bounded by constant times epsilon, which means that this sequence is also Cauchy in terms of the 0 norm. And therefore, well, what is the 0 norm? The 0 norm is the sum from 1 to n of alpha j xp minus xk, but this is linear. So alpha j xp, alpha j xq, that this is bounded by constant times epsilon. So we know that for any epsilon, I can find n naught for which this sum is bounded by constant times epsilon for all p and q larger than n0. But this means that, well, the same inequality holds if I fix j. And that means that if I consider the sequence alpha j xp, so I fix j, and I consider this sequence alpha j xp, this sequence is Cauchy. If this sequence is a Cauchy, I get a sequence of real or complex numbers. The space of real or complex numbers is complete. Therefore, I can extract from this sequence a convergence subsequence, or more precisely, since it's Cauchy, I'm sorry, let me say it again. I just proved that by fixing j, I get a sequence alpha j xp, which is Cauchy. This sequence, it's a sequence of real or complex number. This space is complete, which means that this sequence, which is a Cauchy sequence, converge. So I know that for j, for all j between 1 and n, the sequence alpha j xp converge. Converge because it's a Cauchy sequence of real or complex numbers. It converge. Let me represent by alpha j the limit, and let me define x to be the sum of alpha j zj. Now, I claim that this sequence, xp, converge to x. I claim that xp converges to x. And why is that so? Well, because the zero norm, xp minus x for the zero norm, that this is equal to the sum in J of alpha j xp minus alpha j, sum from 1 to n, this sum is finite, and therefore this converges to 0 because alpha j xp converges to alpha j. So this proves that xp converges to x in the zero norm, and since the norms are equivalent, we conclude that xp converges to x in the space X for the original norm, and therefore that the space is complete because we proved that any Cauchy sequence actually converges to a point.